What if I told you we could see inside a solid object while it's being made? Not by cracking it open, but by listening. Listening to the water hidden deep inside. Well, today we're going to do just that. We're diving into the incredible science of using magnets to watch concrete being born, from the inside out.
So let's just start with the central question, because it sounds impossible, right? Concrete is this dense, opaque block. How in the world can you possibly track what water is doing deep inside that thing as it goes from a wet slurry to, rock solid? That's the exact mystery we're going to unravel right now.
All right, so first things first, why do we even want to peek inside? Well, it turns out that the strength of our buildings, our bridges, our dams, it all depends on the secret life of water molecules while that cement is hardening. It's a hidden world we've never really been able to see before.
You might think concrete gets its strength from just sand and rock, but the real magic, the thing that makes it all work, happens at a microscopic level. It's this beautiful chemical dance where water molecules react with cement particles to grow this complex, interlocking crystal structure. And for the longest time, how that actually happened was a complete black box.
So, if a camera is useless, what can we use? Well, this brings us to the most unexpected hero of our story. The tiny, hidden magnets that are packed inside every single water molecule. Yeah, you heard that right, magnets.
To get this, we've got to zoom way in. Subatomic. A water molecule, right? H2O. It's got 2 hydrogen atoms, and the nucleus of each one of those hydrogen atoms is just a single proton. And that tiny little particle has this really cool quantum property called spin. And here's the kicker. That spin makes every single proton act like a microscopic compass needle, a tiny subatomic bar magnet. So all that water inside our concrete, it is literally filled with trillions and trillions of these little natural nanomagnets. And if they're magnets, well, that means we can mess with them using other, much bigger magnets.
So, how do we turn this cool fact into a useful tool? Well, by manipulating these little proton magnets, we can get them to broadcast a signal that we can actually pick up. This is the whole idea behind a technique called nuclear magnetic resonance, or NMR. So we're not seeing the water, we're literally listening to it.
The whole experiment is actually pretty elegant, like a 3-step dance. First, we bring in a super powerful magnet to get all those little proton compasses to point in the same direction. They all align. Then, and this is the fun part, we hit them with a quick radio pulse that knocks them all sideways. We tip them over. And finally, we just listen. We listen for the faint radio signal they give off as they wobble their way back into alignment.
And that whole process of them returning to their calm, aligned state, well, scientists have a name for that: relaxation. It's just them going back to normal after we've tipped them over. And the signal we measure is the echo of that relaxation.
Okay, so we can get a signal from the water. That's cool. But what does that signal actually tell us about what's going on inside the cement? This is where it gets really clever. We're about to decode the water's entire environment.
See, the secret isn't just that the protons relax, but how fast they do it. So what on earth can the speed of this process tell us about where a water molecule is living inside that solidifying block of concrete?
And here it is. This is the aha moment of the whole technique. It all comes down to how much elbow room a water molecule has. Think about it. If a water molecule is just floating around freely in a big open space, a large pore, its protons relax very slowly. But if that same molecule is trapped in a tiny, cramped little space, constantly bumping into crystal walls, well, then its protons relax incredibly quickly. The speed of the signal tells us everything about the water's freedom of movement.
And this isn't just a vague idea. We can measure this connection with amazing precision. Water in big, open pores might take seconds to relax, but in the smaller, capillary pores, it shrinks down to milliseconds. And for water that's actually chemically locked into the solid crystals, the relaxation time is lightning fast. We're talking microseconds. We can tell exactly what kind of home the water is in just by timing its signal.
So when you put all this together, it's not just one measurement. By analyzing all the different signals at once, the fast ones, the medium ones, the slow ones, scientists can create a detailed map of the cement's entire inner structure as it grows and hardens.
And I mean, look at the level of detail we're talking about here. The technique is so powerful it can tell apart and measure how much there is of each type of water. You've got water in the big capillary pores, water in the much tinier gel pores of the CSH. That's the main glue. And even the water that's literally become part of the solid crystals. It's an incredible level of detail.
So the final result isn't just a single number. The computer takes all those different relaxation signals and sorts them out, creating this detailed quantitative blueprint, a fingerprint of the cement's internal world. And by taking these measurements over and over, you can actually watch that blueprint change. You get to see a movie of the concrete gaining its strength.
But maybe the most important part of this whole thing is summed up perfectly in this quote. This type of NMR is non-destructive and non-invasive. Think about what that means. Any other way of looking inside would mean you'd have to stop the reaction or crack the sample open, which would completely destroy the very thing you're trying to study. With this, we get to watch the whole uninterrupted story of concrete's birth.
And that leaves us with one last, really big question. For the very first time, we have a tool that lets us watch the microscopic creation of one of the most important materials humanity has ever made. So, if we can finally understand and map how its strength is built, minute by minute, does that mean we can start to actually design it? Could this be the key to engineering the stronger, longer-lasting, and more sustainable supermaterials of the future?